Hi, welcome to our next session here in our chapter on the random forest algorithm, where in this session here I will now truly introduce and discuss the fundamentals of the random forest algorithm. Okay, we'll understand how this extends the idea of bagging. We'll then spend some time to understand the general idea behind the decorrelation of trees, so the feature subsampling in the random forest algorithm. We'll discuss the effects of I would say the most important hyperparameters of the random forest algorithm, and then discuss whether random forests can actually overfit. Answer a little bit of foreshadowing, yes they can. Okay, so let's start. We have discussed the CART algorithm before, so classification and regression trees by Breimann. That actually has quite a few appealing features. It's quite interpretable, so it's easy to understand, it's easy to explain, because it's a simple decision tree. It is invariant under rank preserving transformations. So as long as we keep the order of feature values fixed while we transform them, so by shifting them, scaling them, or doing any other type of monotonous transformation, the resulting model, the resulting decision tree will not be substantially influenced by this. The location of the split points will vary, but we're basically fitting the same type of model, and particularly a model with the same predictive power and performance. Trees can work with categorical features as they can with numerical features, and they even can work with data where there are missing values present in the features by using so-called surrogate splits. Now, here's a quote from Hasty, Tipsharani, and Friedman, which says trees have exactly only one aspect that prevents them from being an ideal tool for predictive learning. I'm not sure whether we'll go that far, but they say they could be a bit more accurate. They're not the most powerful predictor. The idea of the random forest is to basically attack exactly that problem by creating a bagging ensemble on top of decision trees. We'll see that. I guess this will become somewhat obvious that we'll lose the interpretability aspect of the single tree, but all of these other advantages of the CART algorithm are inherited into the random forest, and we will also create usually a way stronger predictor by ensembling in comparison to using a single decision tree. So how does this work now? We create a bagging ensemble out of a bunch of decision trees. We have discussed how that works, right? So I don't have to repeat this here again. Breimann, when he introduced that, which I think was around 1998, he thought about this a little bit more deeply, and he wanted to figure out whether he could even improve the predictive performance of such a bagging ensemble further. And then he figured out that the correlation among the ensemble members might actually be a problem, or that, to state it more positively, that by decorrelating the ensemble members, he could potentially improve predictive performance. And we'll discuss exactly that now. There is some intuition behind that. How does bagging work? We have our model f hat, and our model f hat is going to be a simple average across capital M base learners. We already know, or we at least have a little bit of intuition, that in terms of prediction error, the variance of such a model, and that the variance here of our ensemble, because that's what we care about, is maybe not the best thing. So if the model is very unstable, if it has a large variance, that's usually also a component in our generalization error. In this case, we actually like the variance of the underlying base learning algorithm, because that's something we can now smooth out over and that we can attack and reduce. But the variance of our resulting ensemble, that should be reasonably small. If that's too high, that's usually a large component also in our generalization error. Now, do we also have an intuition how variance goes down? If we look at some fundamental theorems of probability theory or statistics, we can expect that variance goes down linearly if we average out over capital M random variables, if they are independent. Okay, if things are independent, let's say they are IID distributed, we compute their average, and then we look at the variance of the average in comparison to the average of one single random variable. Variance goes down linearly. Now, can we expect our ensemble members here in our bagging ensemble to be independent? It's likely wrong, right? Can't really expect that because our individual ensemble members will be correlated. And this is because our bootstrap samples are fairly similar, right? We are sampling from the same underlying training data set. The bootstrap data are fairly similar, and this will also make our resulting models somewhat similar and correlated. Now, if that's the case, how about then we do more a deeper analysis of what the variance of our resulting model actually is? Okay, let's do exactly that. So just assume two things. So this analysis here is a little bit simplified, but I guess it's going to be instructive anyway. So I'll assume that, and this is where I'm simplifying things a little bit. So this here is of course a function. These base learners kind of treat them here as a scalar random variable. And I'm assuming they have all the same variance sigma squared. And I'm also assuming they have a fixed correlation between any two of them. And that correlation I'll denote by rho. What is now the variance of our ensemble f hat? We'll just insert our definition of the bagging ensemble. That's just an average over these base learners b hat n. Now, there is now a nice formula for what happens with the variance, even if stuff is not completely independent. If it would be independent, I could now just draw the variance operator kind of in a linear fashion inside of the sum. But here I can't do that because stuff is correlated. But I can use this more general formula here. We have this, which in a certain sense looks a little bit like a binomial formula. So I have these squared terms here, but here I have these covariance terms between pairs of random variables, okay? Can write it like that. And now the only thing I will do is I will insert my constants, my abbreviations. So the variance of b hat m, so that's supposed to be sigma squared. So I'll insert that here. And now there's a sum over m of these things, so it's capital M of sigma squared. I can also insert my correlation here. Now I have to be a little bit careful because correlation is not the same as covariance, but correlation multiplied by the standard deviation of the one variable multiplied by the standard deviation of the other variable, that's the same as covariance, and because they all have the same variance, so it's covariance between I and j m and j is simply rho times sigma, so times sigma squared. Now all of these terms here in this sum, they are now also all the same. It's a sum over, let me check, capital M over 2 pairs. So this is m times m minus 1 divided by 2. We copy over the 2. Oh, and I forgot about this guy here. So the 1 divided by m, that's inside of the variance. So we draw that to the outside. I'm actually already doing that here. This becomes 1 divided by m squared. And now you just simplify things a little bit. You collect terms a bit. I'll remove all of my annoying scribbling here. And then we look at the resulting formula, and that has actually pretty nice structure. It's quite instructive. So we can see here the sigma squared divided by m. So that would be the optimal reduction in variance we could ever hope for, okay, if there would be no correlation. And here, the sigma squared, that's the worst that can happen to us, because that would be no reduction in variance. You could, for example, think of all models being exact copies of each other. So really deterministic copies. Then if you average those, there will be no reduction in variance, right? Because you're just averaging out over all of the same things. Now, this formula here tells us that between this 0 reduction in variance and between this optimal linear reduction in variance, what we get is a convex combination of the two. So you can see the convex combination here by 1 minus rho here and having the rho there. And this convex combination is controlled by the correlation. between pairs of models of random variables. The stronger the correlation, the less reduction you get, the closer you are to this zero reduction in variance. And if, for example, if rho would be 1, then this here becomes 0, and we just end up with this very bad scenario where there's no reduction. And if rho would be 0, there would be no correlation. Then we are in this scenario of, I shouldn't say independence, because we don't know that whether things are normally distributed here, but in this uncorrelated scenario where we get linear reduction. This is somewhat simplified. I'll add a caveat on the next slide. But in general, now the idea is, can we maybe decorrelate trees a bit more to reduce ensemble variance, and that will maybe also help us to reduce prediction error? I guess that is a valid path forward now. And this is exactly what Breimann did. So he now thought about a simple randomization procedure that you could bring into the tree fitting algorithm. So what we are now doing is, when we are fitting our tree, we greedily construct more and more nodes in the tree, we construct more and more splits, and in each individual split, and when we construct that, we search for the best split. And when we search for the best split, we search over all potential features and then over all possible split points to find the one which reduces our risk the most. So the randomization procedure now says, do not search over all features, but only consider a certain subset, and that random subset of the, feasible features you're allowed to look at in split finding, that's randomly sampled again and again per node. You could do this also per tree, but usually this is done on a per node basis. If you look at some implementations, especially in R, this parameter is called mtry. I guess that might be for maximum number of features to try out for finding a split. I'm not exactly sure whether that's the interpretation of the M. And we will only consider these features now for finding the best split. So maybe here this is our complete, let me actually switch my pen tool on again. So that maybe that's our complete data set here. So with our target column here, we might have a bunch of different features. Maybe there's 4, but now we will only allow color and length for this, training data set of measurements of bananas or objects which can be bananas and maybe also something else. And we will now only search over them, okay? And the idea is, I guess that's pretty obvious. So the more we decorrelate, or the smaller we set this mtry here, the more trees become decorrelated, but also the more random our trees become. In the extreme case, for example, for a specific node, and you might have a large number of features, maybe 100, and mtry would be set to 1. So you now pick one random feature, and then you're only allowed to search for the best split point for that feature, which might be a very bad one. It might not carry any information. It might not even be associated with white, but might be something like a noise feature. But you're only allowed to use that to find a split at that node. I guess for a new node, you're going to sample again, but this makes the trees fairly random, and this will also have a negative effect if you overdo that. But hopefully there might be something like a sweet spot in the middle where this decorrelation helps to reduce variance, as we discussed before, but the trees are not becoming super random. And this is usually exactly what happens. I've created here two visualizations, two simple examples. So I use the classification data set, the spam data set. I use this empty cars data set for regression, which we've also seen before. And I'm now varying mtry as percentage of total features in my data set from 0 to 100. And I'm now plotting the cross-validated error of these different mtry settings. And what you can see is that if we set mtry to a very low value, so maybe to 1, then this doesn't work too well, at least in this data set here. So our trees are becoming way too random. We are not really finding good splits anymore in our trees, and then the variance reduction also doesn't save us. And then mtry becomes a bit larger, and that works actually fairly well. And at some point mtry is too large, and this would here for mtry equals 100%. That would be the original bagging algorithm. But you can see that usually there's a spot where we perform actually considerably better than by just fixing mtry to 100% and basically running the original bagging algorithm. So there is some merit, there is some benefit in running this decorrelated version of the ensemble. Quite good default values exist, which have been empirically, I would say, nicely validated. So for classification, very often we set this mtry here to square root of number of features. So that's also due to Breimann. And for regression, we usually set it to a somewhat larger value. So p divided by 3 usually works quite well. I've even, looked at what would happen if I would have used these default settings here for my 2 examples. Turns out, I was quite lucky. They do work quite well here. And especially for the classification case, nearly perfect. For regression, I guess I could have used an even larger setting. The random forest algorithm itself is not, I would say, super sensitive to its hyperparameter settings, and these defaults usually work fairly well. So if you just stick to them, if you don't do any tuning, you usually, I would say, you are not completely wrong in being lazy here and not tuning your model. But if you want to tune a parameter, this feature sampling parameter, this mtry parameter is usually the most important one. So you can tune that, but you usually get, I would say, less improvements than for hyperparameters of other machine learning models. But you can try it. Sometimes it does work and it's worthwhile. We can also control the depth of our trees, or at the very least we can discuss whether we would use somewhat shallow or deeper trees here in random forests. So in random forests we usually use fully expanded trees. So we don't really do any aggressive early stopping of our tree expansion. I think we also talked here in the lecture about post-hoc pruning of trees. Usually all of that is not really done. So the tree is configured in a manner that it's either fully or, let's say, nearly fully expanded. And that is also done in order to increase the variability, the variance of each individual tree, to get more from this smoothing in the bagging procedure. We can control this a little bit, or can discuss the effects a bit. So for example, there would be a parameter which controls the minimum number of observations in each decision tree node. So that's usually called min node size, and that if you are below that min node size, you would not attempt a further split in your tree. So by setting that to a larger value, you can actually restrict and constrain, regularize the size of your trees in your ensemble. The default for that is very often a low value, sometimes around 5. Can also vary a little bit between regression and classification. Usually for regression you set it to an even lower value. I have again looked at what happens on the spam data set for classification and on the empty cars data set for regression. So especially for regression, you can see a very clear effect here that the smaller you set min node size, you could even set this to 1, the better this works. That's exactly like what I said. For classification, you set this to an even lower value, and for even here on the spam data set, it works better if you choose smaller values, but sometimes it can be okay to constrain this a little bit. There are also other parameters to restrict the depth. For example, the max depth parameter. So you can just prescribe a value. So I don't want trees which have more than 100 terminal nodes, or which don't grow over more than 8 levels or whatever. Usually we don't use that too often. So in this Ranger package here, which is a very efficient implementation of the random forest in C++, and which is connected to R in Python, so that's usually not restricted at all. And there are also alternative hyperparameters to control the depth of the tree. You have seen them before, and we studied decision trees specifically, like minimal risk reduction to actually require from a split, from the optimal split, to really perform this, size of terminal nodes, and so on. Here's a further important kind of special hyperparameter, ensemble size. So I discussed this already a little bit. So usually random forests perform better if the ensemble size is quite large. So there are sometimes people that, for computational reasons, mainly construct smaller ensembles. I guess very often also if you do bagging on top of neural networks, but sometimes also people run, decision tree ensembles of smaller size. But very often performance of the random forest is better if the ensemble is large. Of course, this also increases computational costs, but we can fit trees quite efficiently nowadays, even on larger data So that is not super restrictive if your data is not extremely large. But also, if you make your ensemble larger and larger and larger, yeah, that might increase the performance of the ensemble, yeah, more and more and more to a certain degree, but usually at some point we flatline. Yeah, and there are only diminishing returns for this increased computational cost. Usually setting the ensemble size to something like 100 or to 500, that's usually a sensible default. But we can also inspect something like the development of our prediction error when we vary the number of trees, and there are some smarter techniques how to do that instead of just running a naive cross-validation, which is what I did here, because we haven't discussed the so-called out-of-bag error estimation of the random forest. But we'll look at that, I'm pretty sure, exactly in the next session after this one here. Okay, here's some visualization of how our response surface changes when we average over more and more trees. So here you can see if what happens on the iris data set if I just visualize that for two features, and I'm just using one single tree. And because I'm expanding the tree, yeah, nearly maximally, you can also see that the resulting model, it doesn't look fairly nice. It looks, I would actually say, quite overfitted and, yeah, also somewhat unstable. If you run that again, maybe with a different, I shouldn't say seed because the decision tree algorithm is actually deterministic, but yeah, maybe I would bootstrap the data a little bit, I would wiggle around the data a little bit, the tree might look, yeah, somewhat different. And now what happens if we use 10 trees? Yeah, we see the response surface becomes smoother. And here is 500 trees, so that would be the default in most of the implementations I know in R. You can see something else which is quite interesting, right? You can see the decision boundaries between classes. So they have become, I would say, fairly smooth, fairly appropriate. You can also see how the underlying surface of the probabilistic classifier looks like. Yes, I'm trying to show this again through this alpha blending here. So colors become, yeah, more blended towards white. If the probability distribution becomes less crisp, less clear, and it's not so clear which class we would predict. And especially if you compare this here with the first single decision tree, you can see, and you should know this by now, that decision trees can only perform these axis parallel splits. We can do a bunch of these, but in order to get something like a decision boundary, which is more or less something like a diagonal line here between these two classes, and I guess the green one is versicolor, that's not so easy to produce with a single tree. With the random forest, we're actually getting pretty close to that because we're averaging out over so many of these, I don't know, step functions from the individual trees. There has been a certain discussion in the literature whether random forests can actually overfit, and sometimes that's, I would say, a bit misquoted, the discussion. So Breimann also began discussing that and thinking about that, and sometimes this is reported as random forests can't overfit. That really is wrong. So random forest really can overfit, as can any machine learning model. So what we actually mean sometimes by this statement, random forest cannot overfit, which we probably should not phrase exactly like that, is that A, they are less prone to overfitting than individual decision trees, and that's because this randomization of the trees and the resulting averaging helps. The other thing, what we usually want to say is that they can overfit, but usually what does not happen is if we run the algorithm for a longer and longer time, and by that we would mean we increase ensemble size more and more and more, then this increase in ensemble size usually does not result in relatively more. Yeah? So it either makes our model better or we flatline, but we will not become worse. This can actually sometimes still happen. It's quite unusual if you want to look into the details. There's a paper here by Philipp Probst and Anlor Bolestix, so colleagues of mine, who looked at this a bit more in detail and then published this in JMLR. These are, I would say, not really usual scenarios or not very common ones. So usually what happens is something like this here, where increasing the number of trees just doesn't help us a lot after some point. So we flatline. We'll still spend more computation time for this, but we will not really begin to overfit. So it's not really this usual U-shaped curve we see when we and we might increase complexity of our model. The thing is, I guess it's very debatable and whether we're really increasing the complexity of our model by increasing the number of trees, because we're not really running something like a boosting algorithm here or some iterative optimization. When we add in more trees, we're just adding in a further randomized ensemble member and then just averaging out over things. So we're not optimizing with respect to what's already there and aggressively reducing our loss. Also, if you think about the algorithm of the random forest and bagging in general, the loss function is not really an input to that. So that's the input to the base learning algorithm. We just do the averaging and we just do the variance reduction. Yeah, I guess final slides. So here's one further example. We looked at this before. So we looked at bagging for logistic regression, what effect that has, and for K and N, and for the card algorithm. And here is now the random forest. So that's the bagging, but enhanced with all of the things I explained here in this session. So the simple randomization plus the full expansion, and that actually works drastically better here on this. What is it? It's again the spam data set. Okay, so here you can really see the usual quite nice, quite good performance of the random forest in action. Yeah, and we took good care that the ensembles are all of the same size. So it again is 100 base learners for all of the bagging ensembles, but also for the random forest. Short summary. I'll do that very briefly because I guess we did that quite well in this session. So most of our advantages of the trees, they inherited into the random forest. So we don't have to do that much pre-processing because it's a tree-based ensemble. The algorithm is actually fairly easy to parallelize. We didn't discuss that, but that should be obvious. It's a loop over independent things. The bagging also, as we can easily distribute this to multiple CPUs, so multiple cores. It really often works well enough. So if you do a reasonable approach for a given data set, where you would maybe start with fairly simple models, so maybe linear models, maybe trees, maybe GAMs, and they don't work well enough, and you're a little bit unhappy about that because you would like to actually use an interpretable model here on that task, but the models are not good enough, and you also do care a lot about predictive performance. I guess my next try would usually always be a random forest, because they very often perform fairly well, and you can often get away either without hyperparameter tuning at all, or you can do fairly simple, not too expensive, not too complicated hyperparameter tuning, maybe just of mtry, maybe just of mtry. They often work quite well on high-dimensional data, so there are many people from biostats, bioinformatics, with maybe, gene data or something like that. They like using random forest in these domains as well, and can also work quite well in scenarios with higher noise. They do have some disadvantages, though they have the same extrapolation problem as for trees. So trees, in regression it might look like that. It actually not look like that. At some point we can't really extrapolate very nicely from this if our data ends here, right? So we just continue this flat prediction behavior. They are obviously harder to interpret than trees. So many extra tools are nowadays available for interpreting random forest. So there are things like feature importance techniques that have been, actually many of these model agnostic techniques that we nowadays like to look at interpretable machine learning and in XAI, quite a few of them have actually been developed specifically in the context of the random forest or for the random forest. And then sometimes the implementations can be somewhat memory hungry because you're creating an ensemble over trees and you might be a little bit unhappy about, prediction time, because if you predict an observation, you have to push it through that complete ensemble for not super large scale data sets in training or in prediction. So usually this is not an issue. Yeah. So for many, I would say fairly realistic and normal data sets, that's not an issue. If you're creating an ensemble of, 50,000 trees and you have to stream in prediction over a super large database, maybe you want to worry about that a bit, but for many applications, this is not an issue. Okay, I hope this session was not too long and you could still follow along nicely. This concludes our session on the random forest algorithm here. See you in the next one.